Hi, this is Hafalir. I'm going to present our paper, Efficient Market Design with Distributional Objectives, co-authored with Fuhito, Kojima, and Bumin, Yenmez. So let me start with a quote from John Maynard Keynes. He said, "The political problem of mankind is to combine three things: economic efficiency, social justice, and individual liberty." So we take this quote to a two-sided matching context. So in this context, we can think about social justice as improving a distributional objective on agent types. So when I say agent types, I mean like there will be agents and they may have different types, for instance, in terms of race, gender, socioeconomic status, etc. And we may have some distributional objective on the how these types are allocated in the matching. Economic efficiency is kind of the standard Pareto efficiency. So formally, economic efficiency or constraint efficiency requires that when we have a matching, there exists no other matching that Pareto dominates this matching without undermining the distributional objective. The individual liberty, we can think of this as the standard individual rationality, which means no agent should be worse off compared to the outside option. To Keynes' list, we add strategy proofness. So strategy proofness is important because when we consider a mechanism, that mechanism may result in good outcomes in terms of reported preferences, but if the reported preferences are different from the true preferences, then the outcome may not be a good outcome with respect to the reported preferences. Once we have a mechanism being strategy proof, then we can kind of guarantee that the outcome will be also good in terms of the true preferences. So in a sentence in this paper, what we do is as follows. Given initial matching and a distributional objective, we study existence of a mechanism that satisfies these four properties. What are these properties? Weakly improving the distributional objective with respect to the initial matching, satisfying constraint efficiency, individual rationality, and strategy proofness. So our contribution in this paper is that we first observed that for some policy distributions, this is not possible. So there exists no mechanism that satisfies these four properties. And then we kind of look for a sufficient condition on the distributional objectives such that we will have a mechanism that satisfies these properties. And the sufficient condition we came up with is called pseudo M-natural concavity. I will tell you the definition in a few slides. When the policy objective satisfies this condition, then we provide a top training cycles mechanism that this mechanism satisfies all the desired properties. And in the later parts of the paper, we also provide practically relevant distribution objectives that satisfy our sufficient condition of pseudo M-natural concavity. All right, so there are many applications to our model and setup. One is inter-district school choice that we have studied in our recently published paper, but there are others such as civil servant matching, teacher assignment, Japanese residence matching, worker and tuition exchange, and more. Okay, so let me start with the model. So we have a finite set of schools, students, and student types. Each student will have one type, denoted by tau s, and each student will have a strict preference relation over the set of schools and being unmatched, which is denoted by the anti-set definition here. And each school will have a capacity of QC, and in a matching mu of S will be the match of the student, and this can be either a school or being unmatched. The initial matching is denoted by mu0. All right. So what's a distribution? A distribution is denoted by Xi. Xi is a vector where the XTC denotes the number of students of type T who is assigned to school C. Okay. And so given a matching mu, the distribution induced by mu is denoted by Xi mu. And we say that the distribution is feasible if the total number of students assigned to school T is not greater than the quota of school T. And the set of distributions, feasible distributions, is denoted by capital Xi0. And a distributional objective is then a function from Xi0, capital Xi0 to real numbers, such that when you have f of Xi is greater than or equal to f of C prime, this means that the distribution C satisfies the distribution objective at least as well as the distribution C prime. So another important definition is that given the initial matching mu0, we say that mu weakly improves the distributional objective upon the initial matching mu0 if f of C mu is greater than or equal to f of C mu0. Okay, so these are, in this slide, we have quite standard definitions. Constraint efficiency means that when we consider matching mu, this mu would be constraint efficient if it satisfies the distribution objective, which means that it gives a value f greater than mu0, and there exists no other matching that Pareto dominates this matching mu and also satisfies the distribution objective upon the initial matching mu0. The second one is individuality, which means that each student will prefer her outcome in mu to her initial outcome in mu0. This is standard. And a mechanism phi will take the preference profile of the students as an input and will produce a matching. Okay. And then this a mechanism phi satisfies strategic closeness if no student can misreport her preferences and get a strictly more preferred outcome independent of the behavior of the others. So this, in other words, for each student, truthful revelation is a weakly dominant strategy. Okay, so let me start with the impossibility result. So since this is a short presentation, I will not be able to tell you all the details. But here in this example, we have 6 schools. Each has a capacity of 1, 6 students, and there are 3 types. Okay, and then in this example, the initial matching is given by Si for each I from 1 to 6 is matched with Ci, and you can see from the student preferences that there are actually only 2 matchings that are constraint efficient. So, and these are given by mu and mu tilde here, and you can check that when we consider a mechanism that results in the outcome mu, there exists one student who is strictly better off by lying about preferences, and similarly, when a mechanism gives an outcome of mu tilde, then there exists another student who can benefit from this outcome. So this is a result that shows that there exists no mechanism with the desired properties. So the question is, what is a sufficient condition for on the distributional objectives, such that when the sufficient condition is satisfied, we have a mechanism that satisfies the 4 desired properties. Okay, and the notion that we have is pseudo M natural concavity. Okay, so here we have a formal definition, but again, for a short presentation, rather than giving you the the technical parts, let me tell you intuitively what it means. Pseudo M natural concavity is basically requiring that when we have 2 distributions, C and C prime, C tilde, when we make these distributions closer to each other, and this can be made like in 2 ways. One of them is basically we have a coordinate in which C is greater than C prime, and we decrease C and increase C prime at this coordinate TC. That's one way. Another one is there are 2 coordinates in which C and C prime are ranked in reverse, and then we made it close to each other like in a 45-degree way. So this definition is saying not more than that. And when this happens, the minimum of the values of this, the new outcomes that is denoted here, should be greater than or equal to the minimum of the value of C and C tilde. Okay, so this is the pseudo M natural concavity definition. As I told you in the introduction, this is a novel definition that we came up with, but this is actually very related to another definition that is used in the OR literature. It's the notion of M natural convexity. So the M natural convexity again is now about sets, not functions, but sets. So we say that a set of distribution C, which is a subset of C0, which is the set of feasible distributions, is M-convex if when we have two distributions in the set and when we make them close to each other, that those 2 points will also have to be in the set. Our first result is that basically our notion of pseudo M-natural concavity is kind of like a utility, like a function analog of the known definition of M-natural convexity. So this is similar, you can think about this is similar to like when we have a convex, convex sets, like, so there is going to be a corresponding quasi-concave function that represents the indifference curve, right? So it's exactly the same way. Okay, so this our first result tells you that. And let me continue. Now, like our main result is that once our distribution's objectives F satisfy pseudo M-natural concavity, there exists a mechanism that satisfies the four desired properties, improving upon the distribution objective, individuationality, strategy proofness, and the fourth one. And in this hypothetical, okay, so how we do that? We do this and by using a top trading cycles algorithm. But for those of you who are familiar with top trading cycles algorithm, we have two sides of the market, schools and students, and then we look for, they each will point to their top preference, and we look for cycles, we execute the cycles. But for this one, we have types and we have distribution constraints. So how would this come into the picture? What we do is we actually have rather than schools on one side, we will have school type pairs on one side, and we will have another option that denotes being unmatched. So the option is gonna be denoted by empty set M-set notion, and the other side will be again students. And we carefully kind of redefine the students' preferences over this new expanded set, okay, which is kind of straightforward. And then the kind of novelty of the mechanism is the permissibility condition of the students. So at a matching mu, a student S with type T is going to be permissible to some C prime T prime if this condition is satisfied. Okay. And if this student, on the other hand, has an initial matching, like has no initial matching, in the initial matching this student is unmatched, then we have another first permissibility condition. So this permissibility condition is kind of like the novelty here is that when we are doing the algorithm when we obey these permissibility condition, then we can make sure that when this mechanism is being run, the distributional objectives will be satisfied. But also, like, it turns out that once we do that, like even at the end of the mechanism, everything will be also a distributional objective, like it will be satisfied in terms of the improving distributional objective, but we will also reach to the constraint efficient matching. Okay, so let me continue. So like this is the standard top trading algorithm. So once you have the permissibility condition, then it's the standard top trading cycles algorithm actually. So each student will point to either a CT, a school type pair, or empty set M set, which corresponds to being unmatched. And then each each school type pair and the empty set M set points to the best permissible student. Okay, and then we find cycles, we execute the cycles, we take them out from the market. In the reduced market, we continue doing the same thing. Okay, and then the top trading cycle algorithm will terminate when there exists no student that is unmatched. Okay, so our result is that when our distributional objective is M-natural concave, then the TTC algorithm satisfies, weakly improves the distributional objective, satisfies constraint efficiency, individuationality, and strategy proofness. Okay, so Then we actually kind of like look at we have two more results on this before going to the applications. The first one is, so think about that we have an ideal set, okay? And the ideal set means like these are the distributions that are the best. But we are also okay to get closer to this ideal set. But what do I mean by closer should be defined in what's called the Chebyshev distance, or L infinity matrix, defined formally as this. So once we have an ideal set, okay, which is M convex, M natural convex, and when we define the distributional objective as the Chebyshev distance to this ideal set, then the top treating cycles algorithm will work. This is the first result. And the second result is what we call discrete matrix, which is like we only consider the ideal set, and the ideal set will get for instance, a value of 1 when it is achieved and value of 0 when it is not achieved. Then the top treating cycles algorithm for this distributional objective will also work. This is our second result. So in the remaining 4 minutes, let me tell you a few applications of our results. So we show that in the main body of the paper, 4 practically relevant contexts actually satisfy our sufficient condition. The first one is the school level quota policy. So here in this one, actually the types do not really matter that much. So we will have, for each school, we will have a lower bound and upper bound on the number of students that is admitted to the school. This will satisfy pseudo M natural concavity. The second one is school level diversity policies. School level diversity policies is now we have types, and for each type, for each school, there is going to be a lower bound and an upper bound, and these lower and upper bounds are type specific. So this will also satisfy our sufficient condition. The third one is what's called the exchange feasibility condition. So for the exchange feasibility policy, we go back to our recent published paper, Inter-District School Choice, and in that paper actually we have not only schools but districts. So there is going to be the schools will be partitioned into districts, and from practically, it's important, for instance, at least in the US, that these districts, their amount of money that they get from the states depends on how many students that they serve. So they really care about the total number of students within the district. Okay, so exchange feasibility condition means that there is going to be kind of like a number, a lower number. This can be KD. This is represented by KD, which may represent, for instance, the number of students reside in that district. So exchange feasibility condition means that when we sum up the number of students assigned to any school within a particular district, it is not smaller than this number. So there is a lower bound on this. It also satisfied. And the fourth one is the combination of school diversity and exchange feasibility. So when we have both exchange feasibility and the school level diversity in the previous slide, and that also satisfy our sufficient condition. In our appendix, I believe we have 2 or 3 more, the policies that satisfy our sufficient conditions. Okay, so very quickly, I'm almost out of time. We have a huge literature on control school choice, matching the distribution constraints, matching distribution constraints with initial endowments, and different applications such as student tuition exchange, refugee settlement, and so on. I don't have time to, go over them in detail, but you can take a look from the slide. So in conclusion, to summarize, we studied what Keynes laid down as the political problem of mankind into a matching context. We were able to identify a general class of distributable objectives under which a mechanism with the desirable properties exists. We argue that pseudo in natural concavity is quite permissive because it is satisfied by many real life applications, and one can come up with more examples that satisfies pseudo-natural concavity. But another like important question is pseudo-natural concavity is only a sufficient condition. So can we weaken it? It's left for future research. And that's it. Thank you for your time. Let me stop sharing and stop recording.